Hi, I'm Jussi Jokinen from Aalto University and University of Helsinki, Finland. This work was done in collaboration with Kochi University of Technology, Japan.
This talk is about the new cognitive model of typing that uses machine learning to generate realistic simulations of how humans enter text on touchscreens. New to the model is that both eyes, marked with green, and finger, marked with blue, are simulated. We use reinforcement learning to optimize the model's behavior while considering uncertainty and bounds of the visual and motor systems. The model makes detailed predictions of movement trajectories, errors, and eye-hand coordination, for example how eyes guide the movement of finger and at times conduct proofreading. Simulated results are remarkably similar to human data across multiple metrics including typing speed. Compare human average of 27 words per minute to our model's 25. Number and type of errors made and corrected in terms of how many backspaces are pressed when typing a sentence and whether these are immediate or delayed. How many eye fixations there are in total and how often the gaze shifts from the keyboard to the entered text for proofreading. Our goal is to provide a theory of touchscreen typing and implement a model that realistically simulates human typing. Behind the model is a theory of how users learn efficient control programs in interactive tasks that involve noise and uncertainty. Touchscreen text entry is an excellent domain for this work. The model is the first to reproduce a number of findings reported at CHI 2020. Among others, it explains the role that our central cognitive system has in dynamically sharing attentional resources between different areas of the touchscreen. The main problem the supervisory control system must deal with concerns uncertainty. Due to the lack of tactile feedback from the keys, fingers' position on the keyboard is uncertain. Constant guidance from the eyes is therefore needed. However, visual attention is also needed, at times, to check for errors. Now the hard problem is this. What is the optimum proofreading frequency? What is the optimum balance of finger speed and accuracy, given that fast typing is, fast, but probably results in more errors? We theorize that touchscreen typing can be explained as optimal supervisory control problem. The supervisor attempts to maximize typing performance. It controls the speed and accuracy of pointing movements, having determined the correct balance on a particular device. The supervisor also allocates visual attention between pointing and proofreading. It is able to make these decisions on the basis of observing the estimated value of these subtasks. For instance, when the finger does not receive visual guidance, its actions become less valuable due to increased probability of a typing error. We used reinforcement learning to solve the question of optimal policy, that is, what actions the supervisor and the subtasks should take in different situations to maximize typing performance. As an illustrative example of the capacity of our approach and the model, here is an experiment where we included a simple intelligent error correction. With a certain reliability, typos are automatically corrected as long as the mistyped key is close to the correct one. Without any explicit instructions, our model adapts its behavior to the changes in the task environment. To conclude, our model is based on the theory of optimal supervisory control. It simulates how visual motor control strategies adapt to keyboard designs. It is able to predict human behavior with new devices without need to recalibrate any parameters. The model can be used to solve design problems. For instance, how will a given intelligent text entry aid impact typing behavior? Or, given individual abilities or disabilities, what type of a layout design is optimal for a given user? Please find the paper, the model, and more material from the project website.